All right, so here, after talking about Ohm's law and resistance, one thing that we can take a look at is if I took certain pieces of metal, let's just say I grabbed a metal off of the ground and I attached it to a battery, okay, I can measure its performance. I can measure how it performs when I apply a voltage and I measure the current. I can see how changing the voltage or the potential applied to that conductor is going to affect the current. Okay, and if this is a very normal piece of metal, it should obey Ohm's law. And if you remember, Ohm's law looked like this from our last video. Okay, it was the ratio of potential applied to the current. Okay, I can also rearrange that formula to, I is equal to voltage divided by R, or I can say I times R is equal to voltage. Those are just three different forms of Ohm's law. Okay, so if I was to put it into this form, for example, where I looked at how does a change in my voltage on the x-axis affect my current, I would see that they're directly proportional, and I would expect that I would get a straight line. Okay, so this is what we would call an ohmic graph. Okay, it's an ohmic conductor. Okay, it obeys Ohm's law. All right, and then the slope of that line in the ohmic graph is going to be 1 divided by the resistance. So if I measure the slope, I can take the slope and I'd say it's 1 divided by resistance, so I can calculate the slope of the graph. And that would be something for like a very nice piece of metal, like gold. A good conductor always obeys Ohm's law. But what happens if I did this experiment and the graph doesn't look like that? So if I took a piece of tungsten metal or graphite and I did the graph, I would notice that the graph has this kind of a shape to it, where it looks ohmic, all right? So this part over here is nice and straight. So I would say that let's get a better color, that is ohmic in that region. But as it starts to curve off, it's no longer linear anymore in these regions. So this is non-linear. Okay, so over there, when it's non-linear, it doesn't obey Ohm's law. Okay, so all of a sudden over there, I would say that this part here is non-ohmic. Okay, and there's lots of materials that are non-ohmic. Okay, when it's non-ohmic, what's happening is something's changing. The resistance is changing as we're getting to that point. Something's changing about the material. And usually at that point, if I see a non-ohmic region, it's usually the energy is going into something else, such as light. Okay, so when you have a light bulb, okay, here's my light bulb. Okay, and I have a piece of metal inside. That's usually tungsten metal. Okay, and that thin wire, when I get to a certain voltage where it goes beyond non-ohmic, then all of a sudden the resistance is going to change and that wire gets hot and it starts to glow and we start to produce light. So in the non-ohmic region, some of the energy is now going to be dissipated in the form of light energy and not just heat. And that's the difference between ohmic conductors and non-ohmic conductors. So again, an ohmic conductor has a linear current versus voltage graph, okay, where the slope of that line represents the resistance. And a non-ohmic conductor would have a nonlinear graph, okay? And when it gets nonlinear, that means that some energy is being dissipated into something else. It doesn't obey Ohm's law. But if I took the ratio of current to voltage along any of these points, that would tell me the resistance, and it's changing as this is going along, okay?